Well, hello everyone. This is the sixth installment and the last of the semester of the Harvard Sports Analytics Lab and the American Statistical Association section on statistics and sports seminar series. And we're really delighted to have Tom de Cruz with us to speak today. Tom is a software engineer and researcher with a passion for computer science and artificial intelligence. He received his bachelor's and master's degrees at the KU Leuven University in Belgium, and afterwards undertook a PhD at the same university in the Declarative Languages and Artificial Intelligence Research Group, where he researched how to combine soccer analytics and artificial intelligence. Tom has published papers at top-tier AI and ML conferences such as AAAI, KDD, receiving the Best Applied Data Science Paper Award at the 2019 SIG KDD Conference on Knowledge Discovery and Data Mining. And his research has been popularized in various Belgian and international media. In October 2020, Tom received his PhD degree with congratulations to the jury, and now works as a software engineer at Facebook. So just before we start, the way in which we normally manage questions during these seminars is if you have a clarifying question, please raise your hand and we can call on you. But if you have substantive questions on the content, please save them for the Q&A at the end of the talk. And with that, I'll hand over to Tom and we can get started.
Yeah, thanks, Laurie. I hope everybody can hear me okay. If not, just interrupt me and I'll see if I can fix it. So in the next 45 minutes or so, I'm going to try to give you a glimpse of everything I've researched over the past 4 years during my PhD. And it was mostly about trying to learn value and style from soccer event stream data. So what exactly do I mean? Yeah, there we go. What exactly do I mean by learning value and style from event stream data? Well, imagine you're comparing two players, Messi and Ronaldo. Then learning value means answering the question, who is the better player? And like one simple way you could try to answer this question is say, well, Messi has more goals and assists than Ronaldo, so then you could claim that Messi is a better player. But style is more concerned with how exactly each player plays without necessarily saying anything about how good they are. So you could say, well, Messi passes more and runs less than Ronaldo, but whether that is better or worse, you kind of leave it in the middle. You just want to describe their playing style. So, so now you have a kind of an idea what I mean by learning value and style. And we learned this from soccer event stream data. So what exactly is soccer event stream data? Well, this is a special type of data that's collected by a whole army of human annotators who watch soccer matches through special software. And then they write down everything that have all the on-the-ball actions that happen on the pitch. So for example, they see, well, a tackle happened here, and then a pass happened from here to there, and then finally another pass, and then finally a shot. And they all write this down with this special software. And so for each event, they note the player that was involved, the time it happened, the exact location, the type of the event, the team, etc. So now you have a rough idea of what this talk is going to be about. I can also tell you a little bit about myself. I think most of it was actually already mentioned by Laurie. So this is a picture of me. I'm Belgian, lived in Belgium all of my life. This is this little tiny dot in Western Europe. I've done my my entire education at the KU Leuven University, both bachelor's, master's, and PhD. Wait, seem to have a bit of an issue with Zoom and PowerPoint and how they affect each other. So yeah, PhD in computer science, AI, and soccer analytics. Published papers at a number of conferences. Yeah, I also most of my research is published as Python pip packages in the soccer action package. Yeah, if you want to play around with any of the things you see in this talk, you can go look on more information on that. And yeah, as Laurie mentioned, I'm currently a software engineer at Facebook after finishing my PhD in October. So I'd like to first give a shout out to all of the co-authors of the work that I'm going to present. They definitely have been very heavily involved in all of this. A lot of the figures that I'm going to use in this presentation have also been generated by them. And unlike me, all of these people actually still work in soccer analytics. So definitely reach out to them if you would be interested to hear more about what I'm going to talk about today. Then finally, some interesting links. Pretty much everything I'm going to talk about today, all the papers and slides and the codes are available on my personal website. And we also have somewhat popularized versions of our papers as blog posts on the website of my, the research team that I used to be a part of. Okay, with all those things out of the way, I'm going to discuss, like this is the rough structure of the talk. I'm first going to try to convince you that learning value and style from event stream data is actually quite hard. And I'm going to outline a number of challenges. Then I'm going to talk about how you can, what the best way is to represent event stream data. And then I'm going to go into exactly how we try to learn value and try to learn style. So first, the challenges. Or the alternative section of this title, of this section is 13 reasons why soccer analytics is really hard. So I'll just get right started with the first challenge. The first challenge is that soccer has continuous gameplay, and it's quite hard to divide the game into distinct phases that you can analyze. So this is less of an issue in a sport like baseball, where there's a much more natural start-stop gameplay. Second is that soccer is a team sport, so you have many complex interactions between teammates. And also the role a player plays in his team can change depending on what the situation on the pitch is. But if you compare this to something like tennis, then you don't have to deal with all these issues. Then a big issue is that soccer is quite a low scoring sport. So it's often a lot more luck-based than other sports. And there can be quite a low correlation between how well you played in a match and whether you actually won the match or not. And again, yeah, this is less of an issue, I think, in basketball, which is a much more high-scoring game, and there's often there's usually a bigger correlation between player skill and the outcome of a match. Then the fourth challenge is related to data, which is that the data we're going to use is not always optimized for analysis. These event stream data can contain some irrelevant events like referee changes or weather changes. Some providers of this data don't record certain events. So actually between this pass and a tackle, we're reasonably sure that a dribble happened there, but this is not mentioned in the event data. So you just kind of have to think about that yourself. Okay. And then the last reason why event stream data is not always optimized for analysis is that when you actually expect this data, there can be some kind of an information overload. Like you can have over 200 types of qualifiers per event. And while like individually, they all have their uses. If you try to account for all of them in your analysis, then you just get swamped. So, and it's not very scalable. Then the fifth big challenge is that this data suffers from vendor-specific terminology. So you have multiple companies that collect this event stream data, like Opta, Wisecout, StatsBomb, and Instat, and they all use their own terminology. So for example, like the act of trying to pass your opponent, like some vendors of data would refer to this as a dribble, and some vendors would refer to this as a take-on, and then or the act of trying to shoot the ball into the goal. Most vendors would refer to this as simply a shot, but then other vendors actually have 4 different events for this type of event based on what the outcome was. So this makes that if you write code to analyze data from one vendor of event stream data, it's not easily transferable to data of another vendor. Then the sixth challenge is that regardless of which vendor you pick, usually this data tends to have a quite complicated and dynamic structure. And so you can't really easily inspect this. You already have to write quite a lot of code in Python or in R just to be able to inspect the data and get some basic insights out of it. Then the seventh challenge is that these events have both discrete and continuous attributes, and most models in machine learning or artificial intelligence like to work on either one of those two exclusively. So either purely focus on discrete attributes or purely on continuous attributes, but there are actually few models that work really well on like on a combination of these two types of attributes. Then the A challenge is that there's no exact repetition in data. So you can have phases that are kind of similar, but you're never going to get phases that are exactly the same. So you have to think about smart ways to aggregate over the data. Because nothing is ever repeated. Then the 9 challenge is that you should definitely augment the data with some domain knowledge. So for example, if you're trying to build a very basic expected goals model, which tries to predict what the odds are of a shot going in, then one piece of knowledge that's probably quite relevant is where exactly the goal is. That could be quite useful for your model to know. And also the playing direction is also quite useful for that model to know. But the problem is that it's not always trivial to know in advance what type of domain knowledge you need to add. It's usually when you try to run something, when you try to run a model, and then you expect the results, and then you find out, oh, I actually should have added this piece of information because the results I'm getting now are quite nonsensical. Then the 10th challenge is that the data often, depending on the provider, but in all providers, you're going to get some annotation errors. What exactly are these annotation errors? Well, imagine that you have a dribble, and then like 10 seconds later, you get a tackle, and then you have no idea what happened in between. Or, the phase goes on, you have a tackle, you have a pass, and then a pass suddenly somewhere in a weird corner of the field, and then finally a shot to the goal. So in the first annotation error, it was probably just a missing event, while for the second type of error, that was probably just that pass receiving an incorrect location. But these are really hard to try to, let's say, to try to detect or correct in an automated way. Then fine, the 11th challenge is that event stream data is by its very nature very incomplete. So you know that the specific person passed the ball to a specific location, but you actually have no idea where the other 21 players are on the pitch. So this is, I'd say, like the biggest disadvantage event stream data has compared to tracking data. And it's just something, there's no real way to solve this problem. You just always kind of have to like be mindful of it when you're interpreting your results. That you always have a very incomplete image of the context in the field. Then the 12th challenge is that usually in soccer analytics, there's no real ground truth. So, in a typical task within artificial intelligence, like let's say you have to recognize pictures of cats, then you get some data, you get some images, and then, well, the left one is a cat and the second one is definitely not a cat. And then you can train your models, you can inspect whether your model that is supposed to recognize pictures of cats is doing well or not. While in a typical sports analytics task, which is like determine the best player between two players, there's no real ground truth available. So you have to, you have to default to like some more proxy metrics, like for example, salary, or just make lists and pass them to domain experts to inspect whether your model makes sense. And then the final challenge is there can be a bit of a communication barrier between people actually involved in clubs and then the analysts on the other side. Like you can build a very fancy model that does exactly what you want. And then the coach can say, well, why should I trust you nerds? You never played the game yourselves. And then if you're an analyst that is not very mindful of this communication barrier, then you might respond to the coach like, well, why can't you simply understand that my model is perfect and your opinion is wrong? So those were the 13 challenges. And I find that like being mindful of these challenges can definitely help you in building new analysis tools, like knowing, okay, how exactly am I solving this challenge? Are we solving this other challenge, yes or no? So those were the challenges. So hopefully I've convinced you that my PhD was not that easy. So now I'm going to talk to you a little bit about how you can about an alternative way of representing your event stream data to make some of these challenges a little bit easier. So we've created this language called SPADL, which simplifies and unifies the existing event stream data formats from multiple providers. So rather than having to deal with this vendor-specific terminology, we've come up with a kind of unified representation, and we've released converters to convert Wildcard data, StatsBomb data, and Opta data to our unified representation. The fact that we just get rid of all the irrelevant events that we don't care about by purely focusing on the ball player actions. And rather than storing our data in a very complicated data structure like JSON or XML, we simply store the same 8 attributes for each action and store our data in a table this way. So especially this last point is a huge advantage because you can download data, apply our converters to it, and then you can just inspect your data in a data frame or even an Excel table, and it just gets you up and running to like the interesting results a lot faster than if you would have to write all of these preprocessors yourself. So that's so that was how you can represent event stream data. So this is one of the contributions of my PhD. Now I'm going to go into how you can learn value from these from event stream data. So the goal here is to give a value to each on-the-ball action. So given some event stream data, like a shot, a pass, or a dribble, the idea is to assign a value to each on-the-ball action that expresses how valuable that action was. So this has, pretty obvious applications in player scouting because you can then value a player by just aggregating the values of all his actions. But you can also use it in match preparation to find out like who are the most dangerous players on the opposing team who create the most value for their team. So this is just I've published like 3 papers on this topic, but I'm only going to talk about the last one because I think like the first 2 were more like attempts towards this, while the last paper is like a system that I'm quite happy with, and I think is the best one out of these 3. So why exactly is this a hard task? Why can't you simply value on-the-ball actions? Well, in a soccer game, there are roughly 1,600 actions, depending on your provider. And so here they all are. Here you have your 1,600 actions. And the most common final score in soccer is 1-0. So that means that out of these 1,600 actions, one of them was a goal, and all the other actions did not lead to a goal. So how do you go and value all these other actions? So this is really an issue. So here's an example. Here's a pass from Messi to Busquets. Look, you have a pass here. Okay, so this pass happened, and now we have to evaluate. Okay, was this a good pass? Was this a bad pass? Well, the answer is we don't really know because it's not like a goal was scored immediately afterwards. So you don't really know. So the only thing that this pass did is it moved the game from one state to another state. So you have your game state, you have your action, and then you have your other state. And this is something we can exploit. We exploit this in our VAPE framework, which stands for valuing actions by estimating probabilities. And this VAPE framework is basically leveraging the intuition that an action is good if it either increases the short-term probability of scoring and or decreases the short-term probability of conceding. And then our VAPE formula is just basically putting this intuition into an explicit formula. And while this might seem very simple, it's actually quite a powerful formula, because what this allows us to do is it allows us to go from a subjective task, such as valuing actions, where there's like no real clear ground truth, to an objective machine learning task where there is a clear ground truth. So the objective machine learning task we have to solve is to, given a game state, estimate the probability of a team scoring and conceding shortly after that game state. So, to address any machine learning task, you need 3 building blocks. You need your features, your labels, and in our case, since we're interested in probabilities, we need a probabilistic classifier. So now I'm going to explain these 3 building blocks that we used in a bit more detail. So, okay, so here are, as features that describe a game state, we have 3 categories of features. We have our very simple features, which are just all directly copied from our SPADL representation that I just mentioned. We have some more complex features, such as distance to goal or the time difference. So these are the category of features where the real feature engineering comes into play, where you try to exploit as much domain knowledge you have about the game as possible. And then finally, we also use some context features, such as what is the goal score of the team, because we know that teams are play differently if they're 3 goals ahead or 3 goals behind. So now we have our features to describe game states, but now we need labels that capture the limited temporal influence of that game state. So what exactly do I mean by limited temporal influence? Well, very simply put, if you have a game state, a particular situation on the field at a particular time, and then afterwards a pass happened, and then immediately afterwards a goal is scored, then you can say that, well, this initial game state here probably had something to do with that goal being scored. While if you have a game state and then 10 minutes later a goal happened, then probably that game state didn't really have any effect on that goal being scored. So what we do is we come up with these labels, which simply says that we label a game state as having led to a goal if a particular team has scored in the next 10 actions, and we label a game state as having led to a conceded goal for a specific team if that team conceded in the next 10 actions. So why exactly 10 actions? Well, it's a quite arbitrary parameter, which you can play with depending on what your idea is of the influence of a game state. But actually, you found from experiments that if you any value between 5 or 10 actually kind of leads to the same results. Okay, so now you have your features, now you have your labels, then you need a probabilistic classifier to learn the relation from the features to the labels. And we didn't really do anything fancy here. We just tried out a couple of different very basic classifiers, like most of them you can find in the scikit-learn package. And also tried XGBoost, which has really remarkably good performance on pretty much any tabular data you throw at it. So we ran some experiments. XGBoost was the best one, so we did. But I think this is out of the 3 building blocks, this is the least interesting one. So yeah, now you know how exactly, you kind of know what these VAPE values are and how we compute them. So here's a bit more of an intuitive illustration of these values. So you have a phase, you have Busquets passing to Messi, which is pretty neutral because it doesn't really raise the odds of scoring. Then this pass goes backwards, so it actually decreases the odds of scoring. And then Busquets does a true ball to Messi, which gets a slightly positive value. Then now Messi is going to dribble the ball into the penalty box. This gets a high value. And then finally, he's going to pass it to Vidal, which gets almost a 9% increase in the odds of scoring. And then finally, Vidal gets awarded by a VAPE value of 0.83 because he took a 17% chance of scoring and he converted it into a 100% chance of scoring. If he would have missed his shot, then VAPE would have penalized him with a value of minus 0.17 for his action. So, so as I mentioned, once you have these values for your actions, what you can do is you can rate players with them by aggregating all their actions. So let's say you want to buy a new player, and you want to figure out which one of these 2 players you should buy, either Lukaku or Alexander-Arnold. Well, if you use a very naive metric, such as goals and assists per 90 minutes, then it should be quite obvious that Lukaku is a better buy here. But then if you use VAPE, if you try to rate players on all their actions instead, then the story is a bit different. So we can put Lukaku and Alexander-Arnold here on a graph. And then we see that Alexander-Arnold does more than twice the number of actions per match that Lukaku does, but that Lukaku gets a higher average value for his actions than Alexander-Arnold. So simply put, every time Lukaku touches the ball, your odds of scoring a goal go up by 1%, while every time Alexander-Arnold touches the ball, your odds of scoring go up by roughly 0.5%. But to get their total contribution within a match, you actually have to multiply the two numbers. So we actually, because like Alexander-Arnold, his actions are on average about half as good as those of Lukaku, but he does more than twice of them per match. So actually, per match, Alexander-Arnold has a higher contribution to his team's odds of scoring a goal and winning the match than Lukaku. So this is how we construct our VAPE ratings. So we can't just do this for Lukaku and Alexander-Arnold. We can also do this for pretty much all players. So here's a plot of all players in Spain and England in already 3 seasons ago, actually. And you can see here that attackers usually tend to do few actions per match, but have rather high average values for their actions. While defenders are the complete opposite. They touch the ball a lot, but their actions aren't often as dangerous as those of the attackers. And then the midfielders are kind of somewhere in the middle there. And then you have goalkeepers, which don't touch the ball that often, and there are also a lot of things that can go wrong. Basically, if you want to value goalkeepers, you should use something else than VAPE, because we don't really deal with those types of players very well. So on this graph, there are also 2 very particular players, which is Ronaldo, who has a VAPE rating of 0.6, and then Messi, who's a complete outlier in this season and has a VAPE rating of 1.21, which is almost twice as much as that of Ronaldo. And well, you can imagine that if you put out a pretty controversial graph such as this, that some people will protest. And this is, I think, also this comparison between those 2 players is probably the main reason why this research got picked up in a lot of media. So like my research kind of has led a bit of a life of its own. And as happens in the media, sometimes things get twisted a bit. So this article here says that a supercomputer determines who is better between these 2 players. Actually, the entire system can run in about an hour on a modest laptop. So you don't need a supercomputer for that. So as I mentioned, so using these VAPE values, you can construct like who are the best players in a particular league. So here you have the top 5 players in the 2017-2018 Premier League, according to our system. So this definitely passes the eyeball test, but the problem is that all of these players are quite expensive. So if you're a team looking to buy good players, then this list is actually not that interesting. So one other thing you can do is you can consider younger players who tend to be cheaper, and you can also consider a more minor league, such as the Dutch league, and then the prices become a lot more reasonable. So these are 5 players that we identified purely automatically that were, according to our system, the best under 21 players in the Dutch league. But the problem is, so you can see how much they cost in 2018. The problem is, if you want to buy them now, they're a bit more expensive because they have all transferred to big teams and they all cost a lot more. But we think it's quite cool that our system was able to like fully automatically detect that these were really good players, like before it became like complete mainstream knowledge that these are really good players. Okay, so that was everything I wanted to say about learning value from event stream data. Let me check how far I am. I think I'm about 25 minutes on. So now I want to talk a bit about how you can learn style from event stream data. So what exactly do I mean by capturing playing style? Well, given all the on-the-ball actions of a specific team or player, the idea is to capture the playing style of that team or player in a specific fingerprint, so that you can interpret that fingerprint and also compare certain players with each other, find out how similar they are to each other. So this has applications in player scouting, such as trying to figure out whether a player will fit in a team, or also trying to figure out how exactly an opponent plays if you're preparing for a match against them. So so these are the papers I wrote about this topic. And so I'm only going to talk about the last two of them. And the only thing you really have to know from the first one is that we learned an important lesson by doing this research, is that grids are often not ideal to model playing style. And I'm going to quickly explain why. So a very simple way in which you can model playing style is you take all the actions that a player performed, or maybe you take all the passes that the player performed. You simply divide the pitch into a grid, into a number of cells, and then you count for each cell how many actions were performed in that cell. And then this matrix here is basically the fingerprint of a player or a team. And then you can use this to compare. This kind of expresses where on the pitch they perform more actions and where on the pitch they perform less actions. So, however, this approach, while very simple, it does have a few shortcomings. So the first one is that if you pick your grids to be not fine-grained enough, then you can't differentiate between actions that you really should differentiate between. So for example, here you have a shot map of a specific player. And actually, so if you pick your grid size if you pick the size of your cells too large, then all these actions are going to get put into the same cell. So, and this does not express playing style at all. But on the other hand, if you pick your grids to be too fine-grained, then you're dealing with an incredibly sparse matrix, which can also be quite tricky to use, can be tricky to process, to compute, to compare with other players. Picking like the coarseness of your grids can be quite tricky. And then another shortcoming is that like if you use grids, then you have very abrupt and arbitrary boundaries between grid cells. So here you can see that like these top two shots are put into a different cell than this shot here. Well, actually, they are very close together. They are very similar shots, yet they get distributed to different grid cells, which is ideally something you'd like to avoid when modeling playing style. And then finally, just putting a manual grid over your field completely ignores the data distribution of your data. So for example, if you're trying to model shots, then actually all these grid cells here are not very useful, and it's just a waste of hard drive space, basically. So we've investigated two approaches to try to do better than simple grids to model playing style. And the first of those is player vectors. And I'm going to now briefly explain what exactly player vectors are, or at least give the intuition. So the first thing we do is we kind of make a grid that is probably a bit too fine-grained, and it's quite sparse. But then we smooth it with a Gaussian blur so that it looks a bit nicer. That's the first step. Then the second step is that we compress this shot map here, the smoothed grid, with a technique called non-negative matrix factorization. And so what this allows us to do is it allows us to express let's say the shot map of a specific player as a linear combination of 4 very distinct types of shots. So you have here your right shots, your shots from very close to the goal, a shot from the left, and then a shot from far away. And so rather than having to represent playing style as like this huge 50 by 50 grid, you can actually represent shot behavior using just these 4 numbers here. And then these 4 numbers kind of represent how many shots of this type you do, how many shots of this type you do, etc. So, and we can't just do this for shots. We can also do this for crosses, dribbles, and passes. And in that way, we build these player vectors of length 18 that really basically represent the playing style of a player in a very short vector. So here's an example. So here's the player vector of a professional soccer player called Jesus Navas. And you can see that like he has very high values for three components that we discovered with our non-negative matrix factorization, which are a right backline cross, right flank dribble, and a pass from the right flank. So, you know, based on this, based on these components, you could conclude that Jesus Navas is probably a right winger. And then you would be correct. But the cool thing is that we were able to discover that he was a right winger purely based on his event stream data. And we didn't need anybody to tell us to manually label him as a right winger. And so you can use these player vectors to compare players, see how they differ, find out if they have a similar playing style, yes or no. You can use it for scouting. They're a lot of fun. One other thing you can do is you can also compare a player with himself. So here the difference in player vectors between Ronaldo in an early season and compared to a later season, you can see that he stopped doing many shots from far away and from the left and focused more on shots that are closer, to the goal and more from the right. And he also just pretty much stopped doing crosses altogether. So this clearly shows how he evolved from a left winger to more of a central striker. So that was our first attempt to model playing style. However, there were some things in there that we weren't very happy about. And the most important one is that we weren't able to model the direction in which certain actions go. So we weren't able to model the directions in which dribbles go or the directions in which passes go. So then we went back to the drawing board and tried to do something even better. And this approach is called soccer mix. So the core idea of soccer mix is to, rather than use manual grids, is to soft cluster actions, locations, and directions with mixture models. So mixture models have a lot of advantages. So one of them is that because you're doing a data-driven clustering, you don't have the problem of empty grid cells or empty groups. And because they're probabilistic, then there are no abrupt boundaries between groups. Like if you have two groups that are quite close together, and you have let's say an action that kind of belongs to both of those groups, then it's just going to belong like for 49% to one group and for 51% to another group. And so then in that way you can more easily compare actions. So in our first stage of this approach, what we do is for each action type, such as shots, we fit a mixture model with Gaussian distributions to the locations. So here's an example. Here you have like all the shots performed by all the players in our database. And then we train a mixture model with 3 Gaussian distributions. And then we find out, well, apparently you have shots from the left, you have shots from the right, and then you have shots from really close to the goal. So, and in this way, we discover these kind of location groups, and we do this for shots, for passes, for dribbles, etc. And then in our second stage, so soccer mix is a 2-stage approach. And the second stage is that we take each location group of the first stage that we discovered, and then we fit a mixture model to the fit a mixture model using von Mises distributions, and fit those to the directions of the actions in that locations group. So I think this is made most clear with an example. So here you have all the passes that we discovered in the first stage with their starting locations pretty much in the central midfield. And then you can see that the locations go pretty much everywhere. And then we fit these von Mises distributions to them, which are basically circular versions of the Gaussian distributions. So their main advantage is that basically you can model directions that are close to like -2 pi and 2 pi as with the same distribution. And again, try to discover these groups here. So then we find out, well, there are actually 3 types of directions in which a pass can go from the central midfield. Either it moves backwards, or it moves to the left flank, or it moves to the right flank. So that was our soccer mix approach. If you want more details on how exactly it works, some of the mathematics behind it are actually also non-trivial. I suggest you can read the paper if you're interested to learn more about this. So what can you actually do with this, with our soccer mix approach? Well, what it does is you can feed it a whole bunch of event stream data, and it will decompose that event stream data into a number of prototypical actions. So here are, let's say, this is a sample of all the passes in our data sets. And what we automatically discover are these kinds of prototypical passes. Like these are, like pretty much every pass in our data sets can be expressed as a linear combination, or as say like a linear probabilistic combination of one or more of these prototypical passes. We can do the same thing for example, here for throw-ins. Like here we feed all these throw-ins into our system, and then we discover that there are these bunch of prototypical throw-ins. So then we can use these prototypical actions to construct a style vector of a team or player. So how exactly do we do this? Well, we take, like if you take one action and then you feed it into our soccer mix system, then what you get is a probability vector over all the prototypical actions discovered by our system. And then if you want to get a style vector from let's say a player, then what you simply do is you take all the actions of that player, you feed them all into the soccer mix, and then you get a whole bunch of probability vectors, one for each actions. And then you simply sum them together, and then that sum of all those probability vectors, that's your style vectors. And then this expresses how many prototypical actions, like for each prototypical actions, how often a player tends to perform that prototypical actions. So, and then with the style vector, you can compare players. And so we like to compare them visually because there are quite a lot of prototypical actions. So comparing them in a visual way is more insightful than comparing them just based on their raw numbers. So, like if you compare the style vectors of Sergio Aguero and Roberto Firmino, then you find out that Aguero shoots more from the penalty box. Like these are both strikers, but Aguero shoots more, and then Firmino does a lot more dribbles all over the midfield. So from this, you can conclude that Aguero kind of camps out near the penalty box, while Firmino is more of a striker that often drops deep and supports his teammates. So he camps out near the penalty box, and Firmino drops deep and supports his teammates. So you can also use this not just to compare the playing style of a team, not just the playing style of two players. You can also use it to compare a playing style of two teams. So from this graph, so red means that Liverpool does more of these prototypical actions, while blue means that Manchester City performs more of these actions. And you can find out here that Liverpool tends to funnel the play towards the right. You can see this from their interceptions. And Manchester City tends to play higher up the field. And this kind of matches that Manchester City focuses more on ball possession, while Liverpool are more, let's say, better at counterattacks. So one final cool thing you can do with this style vector is not look at what a team specifically did, but look at how they made their team play differently than they usually do. So we've investigated how teams that play against Liverpool play differently in their match against Liverpool than they do against other teams. So we found out that when teams are playing Liverpool, they tend to perform more offsides than usual. So this suggests that Liverpool has a pretty good offside trap. And then also, as you can see here from the passes that teams do, when they're playing against Liverpool, because Liverpool is a very good team, they're usually forced to play more on their own half and much less on Liverpool's half. So so that was soccer mix. So now just to summarize what I've just told you, there are many challenges. I've mentioned 13 of them that make learning from event stream data difficult, but I found that kind of formalizing these challenges and being very mindful of them really helps while doing analysis and investigating your own models. Then there were a number of representational challenges when it comes to event stream data, and then SPADL is a language, a layer on top of commercial event stream data that addresses some of these, and that has converters available publicly online. Then VAPE is a system to value all on-the-ball actions on like all the context that is available within event stream data. And then finally, we've also introduced 2 ways to capture playing style in a more advanced way than simple grids. And so finally, I'd like to conclude with maybe some of the lessons I learned over the course of my PhD, which is I found that getting the representation of your data right and adding like the right bits of domain knowledge has way more impact on the success of your analysis than, let's say, fine-tuning the parameters of the hyperparameters of some kind of neural network. This is, the first one is way more important. Then second lesson is that if you can visualize your data, you should always visualize your data. I can't count how many times I've printed out some analysis results in a terminal or in a table and thought they looked good. But the minute I actually visualized them, often with like a soccer pitch, then I see, oh no, this actually looks completely wrong. Then the third lesson learned is that, you should always focus, like if you have an idea in your head that you'd like to try out, just try to get early results as soon as possible, because, I can't speak for everyone, but when I'm working on something, I make a lot of mistakes. I never get anything right on the first try. So that's why I always try to get output as soon as possible, so that I can visualize what exactly I'm doing wrong, rather, because if I would try to build a perfect system that does everything perfectly right from the start, I would just waste so much time, because that just wouldn't happen. And then finally, I think definitely let's say the end goal of doing soccer analysis is to communicate it to soccer clubs, to have an impact there, to have an impact to other people. And so I think if you can make your analysis somewhat a lot more interpretable to an outsider, to a non-expert, but you might lose like 1 or 2% of accuracy on some metric that might not even matter, then you should definitely always go for like the more interpretable, simpler model. So that was my talk. I hope it was interesting for some of you. And I'm happy to answer any questions.
Great, thank you very much, Tom. You can, give it like Mark, give it a little visual applause, or use the applause button on the chat menu. So now I think we have about 10 minutes for questions. So if you could raise your virtual hand, which you can do from the chat menu, I'll call upon you to ask your question. And so while everyone's thinking about their questions, I'll start off with one. Thank you very much, Tom. So a question about the action value framework. So what kind of metrics did you test for assessing how well your model performs? So for example, say you were comparing 2 different models for measuring action values, how would you quantify which one is producing more accurate results?
So we used 2 metrics in the paper, which is the area under the ROC curve, and then also the Breyer score. So we use the area under the ROC curve because that's like the metric that says that, well, if you have a very imbalanced data set, which we obviously have because like only like 1% of game states actually lead to a goal. So, and then that's the one, it's common knowledge that if you have an imbalanced data set, you should use area under the ROC curve. And then Breyer score, just to, because that's like let's say a very simple one, is just the mean squared error. But actually by thinking about it a little bit more, I'm actually now of the opinion that I should have focused that I should have decided which model to use purely based on the Breyer score, and that the area under the ROC curve actually doesn't matter that much, because I'm summing these action values. So it's really important that these action values are quite well calibrated. And seeing as Breyer score is also a metric that like sums errors, I think that aligns quite nicely with what exactly I'm using these action values for.
Okay, thank you. Has anyone else got any questions for Tom? Mark.
Yeah, Tom, thanks. Really nice talk. A lot of material you worked on. I was actually curious. I know that your action scores are player specific, but there's a whole world of like adjusted plus minus kinds of approaches that account for everybody who's on the pitch. And so I guess what I'm wondering is that, like, if I'm a player and I don't actually touch the ball, but like I'm somehow drawing away defenders, is there some way that I can get credit for that in your approach, or is there some way to address that?
Yeah, so a big issue is that, so in event stream data, we don't have access to off the ball actions, which is exactly what you described. So yeah, correctly giving credit for those is quite hard when they're just not in the data. So we haven't really looked at approaches to also give credit for that for now. I think maybe the last point I mentioned in our soccer mix approach, like a similar idea might be applied there, where you're kind of like looking like not at the VAPE values of your own actions, but you kind of like look at the, yeah, I don't know. It's a really, really hard problem, and I'm not sure. Like in many cases, it might just be easier to invest your resources in trying to get tracking data if you're trying to do that, rather than trying to build a very complicated system that will then maybe get like 0.5% of the context that you would get with tracking data.
Do we have any more takers for questions?
Are you continuing this work at all, or because you're at Facebook, you have to kind of put it on hold?
Yeah, so for now, my full-time job is is not related to soccer analytics anymore. So yeah, definitely for now, I'm kind of taking a break. But like if I have any inspiration, then I might continue to do something in my free time. But again, like all the co-authors I mentioned, like Jesse Davis, Jan van Harden, Lotte Bransen, Pieter Obrechts, Michael van Rooij, like these are all, they all were very heavily involved in this research, and they're all still, yeah, basically their full-time job is still in soccer analytics. So
I'd say one of the things I really like about your work is that you do make all your code publicly available. It's very brave, and also, it's great to see people doing that, because of course, plenty of people write a paper and present nice results from it, but really sort of allowing other people to play with your model and see, look at its strengths and maybe some of its weaknesses is, first of all, it's great for the community, and also it's kind of, it helps really push forward the development of these kinds of models. So one of the questions I had was that, you talked about comparing action values between different players. Have you considered, did you consider looking at the question of, how a player's performance in one league may translate to another? Both in terms of the difference in quality of two leagues, and also perhaps the difference in playing style of two teams, and how well a player might fit, how good a fit he might provide to a new team at a new level.
I myself haven't looked into that, but my colleague, or well, I should say ex-colleague, Pieter Obrechts, he has tried looking into that, trying to build a model to like predict the performance of one player if he would play in a different league. And turns out that's, well, that model wasn't very successful, let's say. Like he basically found that like any Dutch player that will go to the Premier League will probably perform badly, but that's about the extent of what he was able to learn. So yeah, I could be wrong. So apologies to Peter if I'm horribly ruining what exactly his research was, but I think that was really hard to, it's really hard to predict how a player will perform in another league.
May I ask a question?
Sure. Yeah, you can jump in.
Thank you, Tom. This is Ozan. Just echoing Professor Shaw's point earlier, I also really like the booklet, your dissertation booklet. It's great that you make those material publicly available. And my question is that you covered the value action framework and also style framework. It seems to me that those two can be really powerful if we combine them. The value framework kind of tells us about rewards or credits, debits, and the style is more about the spatial frequency, spatial footprint of a player. So if we combine those, let's say you mentioned how Cristiano Ronaldo's style changed over time, but that's more about he was playing on the right and he changed that, right? Now, if we combine these frameworks, we can talk more about, you know, Cristiano Ronaldo was producing more value at that specific location and less value in another location. And a coach, for example, can tell right now where to use a player, right? Like, although a frequency of a player is high in a certain area, he may be producing more value on average in another area, right? Have you done those kind of analysis?
Well, it is the case that I haven't really tried to combine style with value yet, just because of, like, depending on your role within the team, you're just on average going to get, like, attackers just get higher VAPE values than defenders by default. So I'm not sure, like, so the idea would be maybe to, like, give some advice on playing style based on what actions are successful or not, but my gut feeling is that, like, the way these models are right now, that, like, the like in 99% of cases, like, the advice would just be get the ball closer to the goal, which is not exactly a novel insight. So I'm not sure, like, in the current state that let's say the current state the research field is in now when it comes to valuing actions and value and let's say capturing playing style, how useful a larger model combining those two would be. I think it maybe makes more sense in the short term to focus on really getting, like, the smaller models right and really making sure that those do what we want them to do and that we haven't made any mistakes there.
Great. Do we have any more questions? Okay, in that case, let's thank Tom one more time for a great talk. Thank you very much for coming on.
Yeah, thanks for having me. I hope some of you enjoyed it.